Hi all, this is Mr. Yeager for chemistry. We are moving into a lesson on the periodic table and how it's all broken down. Obviously the most important tool we have in chemistry. I mean, pretty much all the information we could possibly get is in this one table. It's amazing what we can do with it and everything. So you'll see that with the next couple of videos. This one's all about the breakdown and the history of it, and then we will move into some trends in the next video. Again, this particular presentation was created by another excellent chemistry teacher, and I mean, it's just so well done. I like to use it myself for my own students. So here we go. All right, so I mean, obviously if you're watching this at home or anything, it's probably pretty good if you'd have a periodic table in front of you. If you're listening to this for the first time, one of my students, and you need to kind of catch up, obviously you'd want to have it with you, have some coloring pencils, other things that you can do to label it. This is also probably a pretty good video to be pausing throughout it so that you can go ahead and do that labeling. So here we go. All right, so, but first, history, okay? So where did the periodic table basically come from? Why was it developed? The first person that basically started seeing essentially trends. I mean, that's what the periodic table is all about, is the fact that there are trends throughout it and there's some clear arrangement of how and why all the elements came to be the way they are and why there's similarities. And so we have a man named Dmitri Mendeleev that he came along first. He created the first periodic table. He actually, you know, he's kind of like the first data miner. I don't want to say he's probably the first, but he really did actually do almost any real chemistry experiments. He was just very, very good at finding patterns. And so he kind of took everybody else's research and findings and created this periodic table. And he looked at it as, you know, he saw that you could arrange these elements as with increasing atomic weight. That's basically the average atomic mass. Is what we're looking at. And when he did that, he could kind of see that there were similar chemical properties if he set them up in these rows and columns. The issue, though, was, well, I mean, I guess it's not an issue so much, but he did leave gaps in where he was like, just, you know, that the discovered element didn't fit, and so he would move it over. So there were gaps in this table where he was like, I know there's probably another element that just hasn't been discovered yet, or I haven't seen the research on it. Kind of a little bit of a jerk though. Like when people did discover the element, he then took credit for it, being like, I knew it was there, and so it was mine. But like, you know, he actually didn't discover it. He just, you know, took it. But he would actually claim he was the one that found it, even though he never actually, you know, necessarily worked a lot with the chemicals themselves. So the other issue we had, that Mendeleev had, is he would make some random exceptions on his periodic table and be like, I'm just going to put this here because it just fit better, even if it kind of broke some of its own rules every now and then, okay, especially farther down along the periodic table. Then much later, about, what was it, 50 years later? About that, 44 years later, a man named Henry Moseley came along, and he rearranged the periodic table. Again, Mendeleev's table was used by chemists for a good 45 years, but he realized if you put them in order by atomic number, which is our modern periodic table, there weren't any, he didn't have to make exceptions, and everything fit very well, and the trends were consistent both in columns and in rows, so that this is now the accepted periodic table. All right, so the way Henry Moseley actually looked at it is he proposed this idea of the periodic law, where the properties of elements occur in regular repeating patterns as their atomic numbers increase. All right. So we're going to see in a moment, the idea is as you go across a row, all right, we obviously change the chemical and some physical properties, like what we see that change. But then as we go to the next row, we see those same chemical properties showing up again as you like go back to the first column and then change consistently across the row. And then you go to the next row and you see the same thing over and over again. And so we call this periodic. Again, the word periodic means something that occurs over and over and over again consistently. The seasons are periodic. Your school day is generally periodic, going from first to seventh period, etc., etc. All right. So so some of the names. Again, we're trying to organize what we call these different parts of the periodic table. The columns on a periodic table, the up and down columns, we call groups or families. And the reason why is because in these groups or families, they have similar physical and chemical properties. All right? Again, they're not identical, but they're similar. Okay? We will see from a chemical property standpoint, they all react very similarly. Maybe some a little bit more reactive than others, just ever so slightly, but they all react similarly. They like to react with the same type of elements. And we also see some general similarities in their physical properties. Okay, so that's groups or families. Okay. A row we call a period. Okay, a row is a period along the periodic table. That's kind of why we call it the periodic table. It's set up in these rows, and this is what Moseley was saying, is as I go across a row, I start going through basically the same chemical properties. Now, these all don't have same chemical properties, but I see how the chemical properties change across the row. And then if I can go upwards. If I go to the above row, the elements above it, they should have the same chemical physical properties. You know, again, similar. So there's this repeating pattern of we see all these chemical properties occur, and then we see them again as we start the new row. So that's why we call them periods. All right. I think most periodic tables are already numbered, but especially the groups. We do have 18 groups. We look at it from 18 columns. Even the ones that are a little bit lower, I know the first two groups are a little bit taller. There's a reason for that. We'll get to a bit later. But we do then count the next group going on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 18. Okay. The periods. We have 7 periods. I think that might be something that has to be written on people's periodic tables. That's not always written on all periodic tables. But there are 7 periods. We will talk about these elements at the bottom. Some people are like, well, what about the 2 rows at the bottom? They technically are in periods 6 and 7 respectively. You can see based on my color periodic table on the screen here. But we've learned that we have to kind of subset them out of it because they actually have their own unique properties, and then it gets repeated. We come back into the periodic table above it to kind of continue on. But you can see how we go from 56 down to 57, all the way through to 71, and then come back to 72 above. So it's still technically arranged in atomic number order. We just have to pull those elements. It's a lot of elements. We're talking about 28 elements down there. But it would shift the whole bottom half of the periodic table if we kept them in there. All right. All right. The word element itself. All right, it's kind of surprising we haven't specifically given this definition. An element itself is a substance that's completely made up of one type of atom. That's what an element is. All right. If something is in its elemental form, it is pure that one type of atom. It is not mixed with anything else. It has obviously that one type of atom with the same number of protons. We could have isotopes of that element altogether, but they're still all the same element. Okay. All right. So on this, we're trying to set up our next kind of situation. We do have 3 classifications of elements. And the way we do this is we draw a little staircase that you can see with that red line there. I'll kind of redraw over it. That starts at B and then is a staircase on down. That kind of goes diagonally down. So down, over, down, over, down, over, down, over. From starting at B, boron, all the way down to AT, astatine. Okay. I do like that we have this line kind of up here too. We're going to see in a moment hydrogen is kind of its own thing. Okay, even though it's over on group 1, and it does have some similar chemical properties with group 1, which is why it's there. All right, we're going to see that it's not part of that group, okay, even though it's in column 1, okay, when we get to that naming of it. All right, so the first, I like to call them classifications of elements, okay, are metals, and these are the most common type of element out there. We're going to see in a moment. All right, these elements, metals, you can see some properties there. They're hard, they're shiny, they're good conductors, they're malleable, which means, again, you can kind of, you can make them into foils, okay, like aluminum foil. You can kind of smash them down and flatten them, okay, but you can also kind of manipulate them quite a bit, even if they are like stronger sheet metal, all right. And then we also use the word ductile to describe metals. So again, those two words we like to use on a lot of quizzes and tests just to kind of really delineate, to kind of show these are metallic properties. Ductile means they can be stretched out into wires. They say they're drawn into wires. I know that sounds like you're drawing them, but what we mean is we can kind of pull them out and make wires with them. All right. They are located on the left side of the periodic table. As I said, they are solid except for one, and that is Hg, which is mercury. Okay, which is mercury, which I'm sure you've heard of before. All right, it's a liquid metal. It's a silver liquid metal. It's really kind of neat to look at, but also extremely poisonous. Okay, very, very bad. All right, so here's kind of, you can see, almost the whole periodic table is metals. All right, so if you get an element, your best first guess would be, and if it's solid, let's say that, your best first guess would be that it is metallic. But you can see that everything we have that staircase, everything on the left-hand side except for hydrogen, and even those elements down at the bottom 2 rows, they are all metals. They all have metallic properties. Okay? All right. We then have our second class, nonmetals. Okay? They basically, I mean, exactly as the term kind of implies, they almost are completely opposite of metals. Okay? They are poor conductors. They of heat and electricity. When you see them, if they are solid, they're not very colorful, okay? Metallic elements are colorful. I mean, you got the silver, the gold, but you also got some other like hues to them that they can be. They can be pink, they can be blue. I mean, there's a lot of neat kind of different colors you get from metals. Non-metals, though, they're very, just like they say, dull, okay? I almost want to call them like a pastel because I think of sulfur. Sulfur is just a very, I mean, it would be like an egg yolk yellow is what sulfur is when it's solid, okay? So it's not shiny or anything else like that. They can be in almost any state of matter. We do have solid nonmetals, liquid, and gases. Again, there's not a lot of nonmetals, but if you said what is the majority state of matter, it would be gases. All right, but there are some that are solids and some that are, there's again one that is a liquid. They are on the left side of the staircase. Okay, so you can see they don't include that staircase. They're above the staircase and everything on the right. Okay, and then also hydrogen. Again, hydrogen is its own little sneaky one over there. The last group is metalloid semiconductors. All right. These are the ones on the staircase. They kind of have a mixture of both metal and metallic metal and non-metal properties. They, again, they're in between being very good conductors and not good conductors. And a lot of that just depends on the temperature. All right. They are things that we do use as semiconductors, so there's actually some very good use to them. You know, silicon obviously has been used in computer chips forever, okay? But they have to be at particular temperatures, and then all of a sudden they work extremely well, okay? So there's your small group of semi-metals, the ones on the staircase there, all right? The ones I really remember myself that I tell students all the time, it's just down the diagonal. Sometimes it's a little tough to remember that germanium and antimony are ones, but it's mainly the ones down along the diagonal. We sometimes say other than, again, this is where it kind of breaks down. We say any element that's basically touching the staircase is a semi-metal, or sorry, a metalloid, but but not aluminum. And hopefully we know that aluminum is a metal. All right, so that leads us to a very, very important term that's going to be used for basically the rest of chemistry, okay? And that is valence electrons. So we know atoms have electrons that are around the nucleus in different energy levels, which we're really going to break down quite a bit this unit, okay? The valence electrons are the outermost electrons in that atom. So they're on the ones that are in the outermost energy level for the atom when it's at that point. Sorry, I'm saying that very poorly. They're just the outermost electrons. I think that's just a simple way of putting it, okay? So you can see with this example here, we have 1, 2, 3, 4, 5, 6 electrons, but I don't include the ones on the inside. I only look at the ones on the outer energy level, that outer orbit. Again, that's not the correct word, but I'm going to say that. This element would have 4 valence electrons. Now the nice thing is the periodic table tells you how many valence electrons there are, okay? Basically what you do is if we look at the tall columns, okay, that's the big thing, we're looking at the taller columns, so not the middle and not the bottom, all right? We can just count across. Every element in the first group is 1. Every element in the second group is 2. Then we jump to the other side and it's 3, 4, 5, 6, 7, 8, okay? Some people can notice that this is group 13, so it's the ones digit in that number. So when you're in group 13, you have 3 valence. Group 14, 4 valence, et cetera, et cetera, et cetera. Man, I can't talk. Group 17, 7 valence, all right? Now, there is one exception here at the very end. Helium only has 2 electrons, and they're both on the outside of the atom. They're both in the outermost energy level of the atom. They're definitely not on the outside of the atom. They're the outermost energy level of the atom, okay? And so both of those electrons for helium are valence, but we'll see helium acts a lot like these other elements that are in group 18. And even though the rest of them all have 8 and helium only has 2, they are all part of the same group or family. So that's the exception there. The ones in the middle, they can vary, as we say. Generally, I just tell people, if you want to take a guess, they're going to have 2 valence electrons. But again, they can absolutely vary. And that's the same thing with the ones down below, okay? Would be 2, but they absolutely vary, okay? When I say that, there are plenty of exceptions, so that's why we're just going to say the middles vary. So all you need to remember is 1, 2, 3, 4, 5, 6, 7, 8, and helium is your one exception. Okay? All right, so here we go. We're going to now go through the different groups, some of the names you need to know, okay? Group 1, also known as the alkali metals. All right, this is where you're going to probably pause and be able to draw it in a little bit. Group 1 has 1 valence electron, okay? You need to know their properties. They're basically silver in color, soft. They're highly reactive. This is something really, really important to remember. They are highly reactive. That is one of the most apparent properties of alkali metals. They are things where if you find them pure and you have them, if you leave them out, they could very well catch fire and even explode, okay? So especially if you get them in water. I mean, even if you throw it right in the water, it'll definitely explode. If you leave them in the air, they could still pop into flames and then possibly explode because they'll react with the water in the air. So you will usually not find an alkali metal in its elemental form. It's too reactive. So alkali metals, 1 valence, soft metals, and sorry about the announcement real quick here. The
sale out front until 8:15 this morning. $5 cash or $5.50 with card or Apple Pay. Thank you.
There we go. You can hear I'm doing this at school. All right. So anyway, they have 1 valence. They're highly reactive in water. Okay. If you want to draw it in now, it would be this first group over that you can see in green. Do not include hydrogen. Hydrogen does have 1 valence, but it's not a metal. It's the elements underneath of it, starting at lithium, going all the way down to francium. The alkaline earth metals, group 2, they have 2 valence. They are also silver colored, generally soft. When we say soft, you can actually cut them with a butter knife, some. They're also reactive, but not as reactive as group 1. And same thing, because they're so reactive, you almost never find them pure in nature. So that would be the second group that you see there. So if you need to pause, kind of highlight them, use a colored pencil, go around them. Those are your alkaline earth metals with 2 valence electrons. The transition metals. This is where we said the number of valence electrons varies. There's a lot of variation that occurs in this section. It's a very large middle section of the periodic table. There are lots of metals there. They have lots of different characteristics. Again, as we go across, we can find some similarities with their chemical properties, so there is still a periodic nature to them. All right? But they are your true metals that you probably know more about, like iron and silver and platinum and plenty of other ones out there. They have high melting and boiling points. Again, they are that large middle section that we have there. All right. I would go ahead and highlight, sorry, I'm seeing this. These 2 should be highlighted as well. I don't know why they're not highlighted. Okay, that last row. All right, inner transition metals. These are the 2 rows at the very bottom, okay? Again, we do this to make sure that we put these do have similar chemical properties as you go across them as well. They're also known as rare earth metals. If we put them in with the transition metals, it would mess up kind of the whole table, so we call them inner transition metals because they're inside the transition metal area. These are labeled as well. The 2, we give them special names by periods. So you have lanthanides and you have actinides. And again, almost every periodic table has that labeled to the left of them. Okay? But together, they are inner transition metals. All right? And you can read through all the interesting properties about them. There's some pretty unique ones. We are finding more and more uses for them. Some of them have very little use. Okay, so it just depends on the situation. All right, so you can see down there, they are your lanthanides and actinides, inner transition metals. All right, we're jumping over to near the end of the periodic table, the last 2 columns. Okay, I'll go back and mention what the other ones are near the end of this video, but this is the next group we're looking at is group 17, and they're known as the halogens. This is where fluorine, chlorine, bromine, iodine are, okay, and astatine, but astatine's so rare we don't talk about it. All right, they're called halogens. They have 7 valence electrons. They are your most reactive nonmetals. So that is a very common question. What are the most reactive nonmetals? The halogens. Just like the alkali metals, they're so reactive, it's very difficult to find them completely pure. They usually have reacted with an alkali metal or something else, okay? So they definitely, they react very, very, very quickly, but they have 7 valence electrons. So you can see them at the end there. I think I'm just going to mention this. These other groups, we don't really get into too much, but they're just named after the first element in the group. So this group right here that I'm pointing at is the B group, the boron group. This is the carbon group. This is the nitrogen group, and this is the oxygen group. And that's it. All right. And we obviously would say those elements in that group have similar physical chemical properties. Boron group would have 3 valence, carbon would have 4, nitrogen 5, and oxygen 6. Okay. Oops, there we go. Noble gases, our last group at the very, very end. They have 8 valence electrons except for helium, which we said has 2. They are extremely stable. They do not react with anything else, or it's very difficult to make them react with anything else because we will learn, are very happy with the way they are. Okay, they don't want to mix, which is why they were given the name noble gases. Okay, we use the word inert to describe them. The word inert just is another word for not reactive. Okay, and so they're at the very end of the periodic table there, and that's it. So that is everything with the periodic table. I hope you colored yours in and kind of labeled them as we went down the groups, and that is everything. Thank you.